Hi and welcome to Maths class. Today we're talking about maximum rates of increase and decrease. And I'm just going to start by talking a little bit about exactly what that means. So what I've got a graph here is a sketch. Now unfortunately the colours don't come through so clearly, but I've got a black graph which is y equals f of x, and then I've sketched in green the derivative y equals f dash of x. So we can see that this black graph has a minimum here, then a maximum, then another minimum, and then it heads up towards infinity. My green graph, which is the derivative, has a maximum here and a minimum here, and then off it goes. So I'm going to just start by talking about some of the key points which we can identify here, and I've marked them with the letters A to E on the graph. Now if I start at A corresponds to a turning point in y equals f of x. So the original function has a turning point at a. That means that when x equals a, I have an x-intercept on my derivative. So for a, I've got f of x has a turning point. So f dash of x has an x-intercept. All right, you can't quite see that. All right. Okay. So if I look at some other points where that happens, it happens again at C. At the point where x equals C, which corresponds to this point on my graph here, I've got a turning point on f of x, which means I've got an x-intercept on f dash. So f of x has a turning point, so f dash of x has an x-intercept. It happens again at E. All right, it's maybe not so clearly drawn here, but there's the turning point there. That's where my original graph has a horizontal gradient because it's a turning point. It's not a horizontal point of inflection, it is a turning point. So at E, also f of x has a turning point. So f dash of x has an x-intercept. But what I'm really interested in are the other 2 points that I've marked in, B and D. B is a turning point on f dash of x. And D is also a turning point on f dash of x. So what does that signify for my original graph? Now, let's look at B first of all. F dash of x has a local max. That means my gradient is increasing to the left of B and decreasing to the right of B and equals 0. My gradient is neither increasing nor decreasing. So it doesn't equal 0. The gradient of the gradient graph equals 0. So when x equals B, my gradient is neither increasing nor decreasing. It's temporarily stationary because this is a stationary point. So my gradient is increasing here. And if I look at the graph, I can see that indeed the gradient starts at 0 here and it's gradually getting steeper and steeper and steeper. And then to the right, my gradient is decreasing. It's getting less and less and less steep to the right of B until eventually it also hits 0, okay, which is going to happen here. And in fact, after C, it turns into a negative gradient. It's still decreasing, all right? So let's look again in between A and C. To the left of B, my gradient is increasing, okay, which I can see in the original graph by the fact it gets steeper and steeper and steeper. To the right of B, my gradient is decreasing, which I can see in this graph that the original graph is getting less steep and less steep and less steep. So at B, f dash of x has a local maximum. In fact, it's a turning point. Now f of x is still increasing at this point. Okay, when x equals b, f dash of x has a local max. F of x is still increasing because I have a positive gradient still. All of this part of the graph has a positive gradient. And I can see that all the way through here, my original graph is increasing. What I have, in fact, is a maximum rate of increase at x equals b. So let's look at that. My graph gets steeper and steeper and steeper and steeper. It reaches its steepest point. Well, it's meant to be where x equals b, but I've drawn it maybe somewhere here. It reaches its steepest point and then it starts getting less steep, less steep, less steep. So what a turning point on the derivative graph represents is a maximum rate of increase, the maximum gradient in between A and C. Not the total maximum, it's a local maximum. Clearly my gradient gets even steeper up here, but this is a local maximum for between A and C. Okay, let's look at D. I've written nothing at D yet, but D on my green derivative graph is a local minimum. So if I look at what happens in between C and E, I need a pencil to point with. I'll just point with this. My gradient here is very flat. It gets steeper and steeper and steeper, but in a negative direction. So my gradient is getting more and more negative. So in other words, it's still decreasing, decreasing, decreasing. Somewhere about here, it turns a corner and starts increasing, increasing. And that's what happens at my turning point here. So at D, f dash of x has a local minimum. At this point, f of x itself is still, now is it increasing or decreasing? Let's look at it. At this point where x is D, f of x is still decreasing, right? It still has a negative gradient. But where this is decreasing less rapidly here, it's decreasing at its steepest on this point, and then it becomes less steep here. So that is, at that point, a maximum rate of decrease. So we have a maximum rate of decrease when x equals D. Okay, so this is a little bit hard to wrap your head around, simply because we're no longer talking about maximum and minimum values of f of x. We're talking about maximum and minimum values of f dash of x and what the significance of that is. So I just want to talk about a few real life examples where we might be interested in maximum and minimum rates of increase or decrease. When my population is increasing, I might need to know whether the rate of increase of the population is itself increasing or decreasing. Okay, it's one thing to know that my population is getting larger, but there's a big difference in a yearly 1% growth and a yearly 10% growth. So I would need to know, when is the rate of my population increase at a maximum or at a minimum? Similarly for velocity. Velocity is the rate of change in location. It's speed. It's how fast I'm changing where I am compared to where I was. It's important to know when my velocity, my rate of change in location, is increasing and when it's decreasing and when it's reached a maximum. What about the rate at which profit is decreasing? If I run a big company and I can see that profit is decreasing, I'm not just interested in the fact that profit is decreasing. How steeply is it decreasing? And can I do something to stop that decrease from getting steeper? Right? So when I've stopped the decrease from getting steeper, then I've I've turned my change in profit. It's still decreasing, but it's not a minimum value anymore, okay? When is the fastest change in depth due to tides? So tide tends to move quickly right in the middle, and when it's at its peak and at its lowest, it doesn't move as fast. And the reason that's important to know is because, for example, in Port Phillip Bay, we have a narrow outlet for the tides there. So at the time when the tide depth is moving fastest, I've got a very rapid current going in or out of Port Phillip Bay. I need to know when is the fastest change in depth due to tides, either the fastest rate of increase of the depth or the fastest rate of decrease. So they're just some examples of when I'm interested not just in how deep is it and when is it deepest and least deep, but also when is the change in depth fastest. So we're looking at maximum and minimum rates of change. All right. I'm not going to do a worked example, but what I'm going to do now is talk a little bit about the second derivative. Now, second derivative is not strictly speaking a part of our course, but having a good understanding of it is really useful. I would say almost really important. Okay, so what is the second derivative? If I've got y equals f of x, then f dash of x is what we call the derivative. But for now, we're going to also call it the first derivative, because if I then derive again, I get f double dash of x. So to make this clearer, if I have y equals x to the power of 4, then dy dx is going to be 4x cubed, and d squared y dx squared, that's the second derivative, is 12x squared. I derive it and then I derive it again. Now you guys have already actually done this when you're looking at acceleration. If I've got x in terms of t, where x is my location, I derive that to find dx dt, or x dash of t, and that gives me the velocity. If I then find the derivative of velocity, I've got acceleration. So essentially, acceleration is the second derivative of location. So let's look again at the shape of the graph and what we can learn from the second derivative. When f of x is concave up, here's y equals f of x, it's concave up. Now we've just been talking about that. When I'm concave up, then not only is my graph increasing, but the steepness of the graph is also increasing. The gradient is increasing, which means the rate of change, f dash of x, is increasing. So if my f dash of x is increasing, that means when I find the derivative of this, I'm going to get a positive value. So if I've got a second derivative and it's positive, that is going to tell me that my graph is concave up. And that tells me that my rate of change is increasing. When my graph is concave down, y equals f of x concave down, that tells me if we look at this graph, it's very steep here and it's getting less steep, less steep, less steep. That means my rate of change is decreasing. And if I find the second derivative, if I derive the rate of change, then I will get a negative value. So when the second derivative is negative, I'm going to get a concave down graph. And there's all sorts of implications for the kinds of shapes we can get. I mean, at the moment, we're all hearing about this idea of flattening our coronavirus curve. A viral growth is at its biggest problem when it's growing exponentially, when the graph is concave up. Because not only is there growth, is there a positive rate of change, but the rate of change is increasing, which is how come we get this concave up graph. What we want is a concave down graph. Even if we're still increasing our cases, we want the rate of change to be decreasing, because what that means is that we're heading towards some kind of maximum, okay, if we follow that pattern. All right. So I've looked at concave up and I've looked at concave down. The third thing we need to look at is our point of inflection. Now, these graphs are both f of x, y equals f of x, two different graphs. And what I have here, f of x is increasing all the time. This is a consistently increasing graph that I've drawn here, except right here looks like it might have a zero gradient right at the beginning. So it's concave up here, then here it stops and it starts to be concave down. I always talk about this as like you're turning a corner. If I was driving, I would be turning my wheel to the left, and at this point I would be straight, and then I would turn to the right. So my point of inflection is the point where I stop turning left and I start turning right. So at this point, f of x changes from being concave up to concave down, which means f dash changes from being increasing to decreasing. And it means f double dash of x changes from positive to negative. So if double dash of f double dash of x, my second derivative, changes from being positive to negative, that means that at that moment it equals 0. I'm going to have an x-intercept on this graph, which means a turning point on f dash of x. In fact, it's going to be a local maximum because I've changed from increasing to decreasing, from going up to coming down. Now this is another point of inflection where everything is in reverse. I start with concave down and I finish with concave up, and this is the point at which I turn. So f dash has changed from decreasing. Here my gradient is decreasing. It's become more and more negative. Right? The fact that it's getting steeper doesn't change the fact that it's decreasing by becoming more and more negative. And now it's changed to concave up, which means that my gradient is getting less negative, which means it's increasing. So f dash changes from decreasing to increasing. Therefore, f double dash changes from negative to positive, which means that at that point right here, my second derivative will equal 0. It'll be an x-intercept on the second derivative, which corresponds to a turning point, in fact, in this case, a local minimum on my derivative graph. So if I go back to the very first graph that we looked at, let's look at D, okay? I can actually see here that as my graph is concave down to the left and concave up to the right, this point D is when that changes, which is why I get a local minimum here on my first derivative. And if I found the derivative of this, well, we all know that if I found the derivative of the green function, I would have an x-intercept here because I have a 0 gradient here. All right, so that corresponds to a point of inflection on this graph means a minimum or maximum turning point on my first derivative, which will be an x-intercept or a 0 value for my second derivative. Now, why is that useful? It can help with sketching, and it can most importantly help with interpreting questions. So if we go back to the things we're talking about, if you are asked a question about when was the change in population at a maximum, when was it increasing the fastest, what we're looking for is a turning point on the first derivative, which means we can find the second derivative and make it equal to 0. That's the easiest way to find a turning point on the graph, is derive it and make the derivative equal to 0. So that's our second derivative. Similarly, if I'm looking for the rate at which profit is decreasing when I get a maximum decrease, which is the steepest negative gradient. A maximum decrease is the steepest negative gradient. When is my decrease at a maximum? When my first derivative has a turning point, a local minimum, which means my second derivative will be equal to 0, and that's the way we use it.